Alright, so we've done this funny thing that we've never really done before, and we did chapters 18 and 19 first, and now we're going back to chapter 17. So there's built in kind of automatically a little bit of review because, well, it's got some material that your book covers first, and so that's not necessarily a bad thing. What we're talking about in chapters 17, 18, and 19 are different models of light, and so up to this point, what we've been learning about is the ray model of light. And the ray model of light is just that. It's a model, right? It's a way of thinking about light and light rays. It's not completely accurate, but for our everyday experiences, it's pretty darn good. And so in the ray model, we talk about like ray tracing and lenses, because this is how light behaves on a macro scale, a big scale. We talked about lenses. We did the thin lens equation. And we talked about microscopes and telescopes. And the ray model is really great for kind of understanding light and predicting what light is going to do when it interacts with substances that we're very familiar with. However, there's another model of light that we really need to consider because it describes light in a much more accurate way, even though it's not readily observable by us as humans. We don't interact with this model a whole lot, but it actually is kind of a better representation of light, and that is of the wave model of light. And so we kind of sort of touched on this in the beginning of class when we talked about the electromagnetic spectrum in our first lab, and how it's basically just a bunch of waves that go from very long wavelengths like radio waves and microwaves to very small wavelengths like X-rays and gamma rays, with visible light right in the middle of that spectrum. Visible light right in the middle. And so what we're going to do for chapter 17 is spend some time just considering why it's appropriate to model light as a wave and why it works, right? And ultimately, at the end of the semester, we'll wind up at the particle model, where we talk about light as photons. But this is some weird stuff that we're not getting to yet. That's the end of the semester. So for now, the wave model of light. All right. Just to give you a picture of kind of how these differ, right? We've been talking about the ray model of light, which you see in the upper left, which is just that. It's like light travels in these big chunky beams, and they go in straight lines forever until they interact with something like a lens, at which point those light rays bend, right? And we get these inverted images and magnified images and all those glorious things we've been learning about. Great. The wave model of light is a little bit different, and so we might go back to what we think about sound waves, or maybe the things you've observed on waves with a slinky, right? And these were these kind of initial properties, which is that waves can refract, and they can bend, and they can interfere with one another. There's constructive interference and destructive interference with waves, and we observe these same things with light, as we do with sound, as we do with water waves, as we do with any other kind of wave. And so even though they're not as easy to see for us as humans as the ray model is, for instance, the wave model of light is still really appropriate. And so this picture, for instance, is of a ripple tank, like the one we've used in class. There's a little motor right here that's making waves. It's moving up and down. Those waves initially travel parallel to one another, but after they pass through this opening that is smaller than the wavelength, they kind of appear to bend, right? And that's this funny property of waves that we're going to call diffraction. Not refraction, but diffraction. And so we're going to go on to define this. We've already talked about these two vocabulary words, reflection and refraction. Reflection is the bouncing off of light. This usually happens with smooth surfaces, so like plane mirrors or convex mirrors or concave mirrors. little review: plane mirror, right? Concave mirror, and other way. There we go. And a convex mirror, right? So there we go. Reflection happens with mirrors. Refraction is a little bit different. It is the bending of light as it passes through something. Passing through. And so I'm going to give you an example down, or maybe up here. If I have a triangular prism and I shine a light ray in, then that light ray might actually bend. Let me think. Maybe I don't want to shine it that way. Let me redraw this. I don't like that picture. Alright. There we go. So let's say that I have a triangular prism. There we go. And I am shining light in, and it bends accordingly and kind of comes out in this funny, odd direction. So as light is going through something and it bends because it changes speed as it enters that medium, we call that refraction. So we've talked about these two. And I'm giving you this new vocabulary word, which is diffraction, right? And be careful because it sounds the same. When a wave spread, and this is when a wave spreads out after passing through an opening, right? Or we're also going to call this later on a slit. And a slit is just a very small opening in a substance that that wave can't pass through otherwise. So like this barrier, right? It's a solid, these little water waves can't get past it, they pass through this slit, and then we see this diffraction happening afterwards. Alright, and then interference is wave, I'm just going to call it wave addition. And there's two kinds, right? There is constructive, S-T-R-U-C-T-I-V-E. There's constructive interference where waves meet up in sync with one another, and because of that, they amplify and make a larger wave. We've talked about this with sound waves, right? But it also happens with water waves, and it also happens with light waves. There's also destructive interference, and you hear that word destroy in there, and that's going to be your clue. And so this is when waves of any sort meet up out of sync, right? So one is having a crest and the other is having a trough, and vice versa. And these meet up to cancel each other out. And again, we see this with like noise canceling headphones and sound waves. We see this with water waves. We see this with slinky waves, and we see it with light waves, right? It's just general properties of waves. So picture for reflection, picture for refraction. And I want to take a second here and kind of elaborate on this whole refraction thing. We did a demonstration in class and I've kind of alluded to it, but in chapter 17 I kind of told you guys just to accept it. Right? Light bends just because. Well, light bends based on the wavelength of that light and the substance that it's going through. So as light passes through a new material, and this is any material besides air or vacuum, it actually slows down and the wavelengths shorten. The important thing to remember here is that the frequency is constant. And remember, frequency, if I've got like a wave traveling, it's the number of crests that pass a given point in 1 second, right? And overall, this causes a bending of light. And so when we did our demonstration, I had you do the same thing. Once you cross the line into, the water, or what we were pretending was water, you slowed down and your steps shortened. But you kept the same pace of step. And I didn't really tell you this part, but I'm telling you now. You kept the same pace of step. And that's what causes it to bend. The index of refraction, this kind of constant that we've just accepted up to this point, actually has a formula that we can calculate. And so if I rearrange this formula, n is equal to the speed of light over the velocity of the wave in that substance. And so this red light is traveling at the speed of light, but then it slows down when it's in here. And so we would call this C and we would call this V. These two things also have different wavelengths. So there's a wavelength in air and a wavelength in glass. But the frequency in air is equal to the frequency in glass. They stay the same. And so you can also find kind of the new wavelength or the new velocity of a wave based on the index of refraction, the speed of light, and the original wavelength in a vacuum of whatever that thing was. And just as a really good reference, on page 547, there is a table of the different indices of refraction that you can use. All right, so here's a nice concise version and a little refresher. Way back, we talked about the velocity of the wave being equal to its frequency times its wavelength. And we also talked about the velocity of light being 3.0 e to the 8th meters per second. When we talk about the velocity of light, this is kind of a longhand way to write it. Because it is a really special thing, it kind of gets its own variable. And so you might see this variable c pop up from time to time, later in the course for sure, in the form of E equals mc squared, right? And that c is just the speed of light. N is the index of refraction. And again, a really good thing to note, because I will grill you on this, when light enters a new medium, the wavelength and the velocity change, but the frequency does not, right? And you might want to make a note, just that easy access table for indices of refraction is on page 547. All right, so on to diffraction. All right, I've given you images for reflection and refraction. We've talked about these things, but on to diffraction. And I've got a wave tank in the class that we can play with and talk about. But what we see is that when this distance between the two barriers is smaller or about the same size as the wavelength, distance from one crest to the next, we get this kind of circular bending of light. And this is actually a really good one too, because it shows interference among these waves. So we see a really strong set of waves here, a really strong set, a really strong set, and then these kind of areas of calm in between. And that's because of interference, right? In these areas where there are strong waves, we are getting constructive interference, constructive interference, constructive interference. Those wave fronts are adding to one another to amplify. And then in these spots where we see very little going on, that's experiencing destructive interference and destructive interference. Those different wave fronts are canceling each other out in those spots, right? With light, it's not as easy as just setting up a barrier in water, because light waves have extremely small wavelengths, like 450 nanometers. That's to the -9, or ranging up to, at the very largest in wavelength, 700 nanometers, right? And so when we're talking about the width of the slit that we would have to have is about this size, it's very, very small. And so when we make these kind of devices through which light will diffract, we call them diffraction gratings. And there's a few different kinds. So there is a single slit, which just has one opening through which light can pass. There is a double slit, which has two very small openings through which light can pass. And then anything more than two slits, we actually call a diffraction grating. And so basically what we're going to spend the next few minutes on in the chapter is predicting how light is going to diffract, how it's going to spread out based on the width of the slit, how many slits there are, and how far away we place our viewing screen. And that's it, right? It's just It's just predicting the pattern that waves are going to interfere. And so we've got each of these situations. For this lecture, I'm going to first talk about double slits, and then I'm going to talk about diffraction gratings. And then next lecture, I'll talk about single slits, and I'll actually talk about circular apertures, which is kind of a different type of single slit. So circular apertures after that. And really all these are is getting to know your variables in the context of a picture. So double slit, diffraction grating, single slit. And after that, it's kind of just a plug and chug. So double slit has its own set of formulas. Diffraction gratings have their own set of formulas. Single slit has their own set of formulas. And the variables are kind of the same for each. So once you know a few things, you can just plug them into the formulas and figure out what you need to know. In terms of what light looks like when we send it through a diffraction, so when we send it through a single slit, what we see on our viewing screen is kind of this one thing, one bright spot, and then a few other little bright spots on the outside, right? And we call this the central maxima. And so these bright spots are where light waves are constructively interfering with one another. So we get constructive interference there, and there's a little bit of constructive interference there. And then the dark places in between them, which we're going to call the dark fringes, are due to destructive interference and destructive interference. When we send things through a double slit, we pretty much see the same thing, only there's more interference going on. So the more slits we have, the more interference. So you still kind of see, the same chunks that you see above, but within those, they're divided up into a bunch of stuff. And so we're going to call this the central maxima. All the bright spots happen because of constructive interference, and all the dark spots happen from destructive interference. And all we're going to do is predict where the bright spots show up and where the dark spots show up, based on the kind of slit we are sending them through and where the viewing screen is. This moves on to a diffraction grating, so single slit, double slit, and then diffraction gratings. And the pattern that you notice is that, the more slits that I send light through, the more kind of defined, I guess, these maxima become. And so they kind of become sharper and sharper, and I can send them through infinitely many slits, and we'll do some problems where there's like 750 slits instead of just 7, but you get the idea. The more slits, the more defined and kind of the thinner these sections get. That's the general pattern. And so diffraction shows interference. When we observe this with light, it supports this wave model of light, and it is observable. It's really inconvenient to do so, and you guys will experience this. You have to look through very small things, and diffraction patterns are extremely small, probably smaller, like fractions of a millimeter wide, but it is still observable nonetheless, and so there is this appropriate wave model for light. So I want you to stop and think about this for a second. What could change the pattern viewed on the screen? So let's say I have a light source back here, like a laser, and I've got a diffraction grating in this. This is actually going to be a double slit, right? And I get constructive interference to produce the bright spots, and I get destructive interference to produce the dark spots. So what could change what I view on this screen? Well, certainly, and I already kind of told you, the number of slits that you have could change what you view on the screen. The width of the slits could change what you see on the screen. And then the spacing between the slits could also change what you see on the screen. And so single slit, double slit, and diffraction grating, these are the kinds of things that we're going to be playing with. All right. So just a little terminology, and page 549 is great for this if you don't like the image that I have here. So on the screen, and this will be our screen, we'll see bright spots and we'll see dark spots. We call this center and brightest spot the central maxima, and we numbered each of these going out. So m sub 0 is the central maxima, and then we say m1, m2, m3, and so on and so forth. And then I can actually say m1, m2, and m3, right? And basically you can think about this as if I'm counting from the center spot, this is light band number 1, light band number 2, light band number 3. We just use the variable m for maxima to describe those. We can measure, on our maxima, we can determine y, the distance from the center that they will be. So like y sub 1 is the distance on the screen, like in meters, that I will see the bright spot number 1. And then y sub 2 is the distance on the screen that I'll see bright spot number 2. Right? We also have this variable L down here that represents the length or the distance between the plate and the screen. And just like you moved the screen to and fro with the lenses, with diffractions you can do this as well, and it'll actually change what you see. We can also talk about bright spots in terms of their angles from the central maxima. So theta sub 1 is the angle between the center line and the first bright spot. Theta sub 2 is the angle between the center line and the second bright spot, right? And again, this depends on L. Last but not least, when we talk about our slits, always be very observant about if you're dealing with a single slit, a double slit, or a diffraction grating. So you do want to pay attention to whether that is a single slit, double slit, or a diffraction grating. The other thing that you'll want to pay attention to is this variable d, and that is the distance between the slits, right? And it'll usually explicitly tell you that in the problem. So here is a big long list of variables and what they mean. So basically all I'm going to do is give you a bunch of formulas and some homework problems to try. But in order to do those successfully, you need to know what the heck all these letters and symbols mean. And here is your list. I suggest pausing the video at this point and copying these into your guided notes. I've also accompanied this with the double slit formulas down here at the bottom, and we'll talk about all of these in just a second. So go ahead and pause the video and take your notes. Alright, so in a double slit interference, there are bright spots, right, which we're calling this variable m. For a bright spot, there we go, we would call this m sub 0, m1, m2, 1 and 2, and so on and so forth, or -1, -2, there we go. And these happen, again, the bright spots are because of constructive interference, and the dark spots are because of destructive interference. Interference shows up like this, and this is another really great view to kind of show you, okay, well, I've got the wavelength, these are distance d apart, and I can talk about maxima in terms of their position or their angle. And so this on the screen would be like y sub 1, the distance to the first maxima. So a quick question, and you'll use this formula for it. Suppose we're viewing a double slit diffraction, and the screen is moved closer. What happens to the interference fringes? And so this is the distance between the fringes, and we're talking about decreasing this number. And so if we decrease the numerator of a fraction, this will also decrease, and we can assume that they will get brighter as well. And so we see that they get brighter and they get closer together if I move the screen up to, say, like here, right? And that makes sense, right? The further I get out, the farther that angle projects, etc., etc. All right. Light of wavelength sub 1 illuminates a double slit, and interference fringes are observed on a screen behind the slits. When the wavelength is changed to wavelength number 2, the fringes get closer together. How large is wavelength 2 relative to 1? So I'm going to use the same formula for a double slit experiment, and I know that with wavelength 1, this is very large, and with wavelength 2, this is smaller. If nothing else is changing, the length or the distance between the slits, then I have to infer that wavelength 2 is smaller than wavelength 1, simply because of that equation. Alright, and last topic for this video is diffraction grading. The only way diffraction grading is any different is we've got this variable n for the number of slits, and so obviously with like single slit and double slit, you know how many there are. For diffraction grading, there are lots and lots of slits, and so this formula is going to be really helpful. The number of slits is equal to the distance between those slits. And so sometimes you're given the distance between them, or sometimes you're given the number of slits. Based on that, you can talk about diffraction gratings. So this D is going to be important. And then theta sub m is actually measured in radians. So I'll tell you, be careful with that. And the sub m is just the order of the maxima. So if I'm looking at bright spot number 2 and the angle for that, we'll just call that theta sub 2, right? So again, take a second and pause the video and copy down your variables and your formulas for diffraction grading. Right? And then what we see is that as n increases, as n goes up, the intensity of these bands also goes up. The intensity of these bands also goes up. And so when we look at diffraction gratings of a laser versus a white light, we see some interesting things happening here. And so for the white light, we have this super intense white medium, but then I'm going to ask you, why do we see this Roy-G-Biv pattern? And well, we see this Roy-G-Biv pattern because light diffracts at different angles, and white light has all the colors of the rainbow. And so we see red towards the outsides, and then blues towards the insides because they don't diffract as much. Alright, so white light passes through a diffraction grating and forms rainbow patterns on the screen. For each rainbow, select one of these that apply and go ahead and pause the video to make your choice kind of in your head on your own. And again, the red side is the farthest from the center because it has the highest angle of refraction. Alright, and here's your homework that we will do in class. So this is from page 569. These first few problems are just about light and waves, and then we move on to double slit and diffraction